Good morning, I am Alessandro Conti and today I will present the work Cluster-Level Pseudo-Labeling for Source-Free Cross-Domain Facial Expression Recognition. This work comes from the collaboration of University of Trento, Center of Mind-Brain Sciences and Bruno Kessler Foundation. In this work, we tackle the problem of domain adaptation applied to facial expression recognition, which means that we have as input a set of facial images, and the objective is to assign to each one of them a label from a discrete output space. The problem is characterized by a long-tail distribution, where a subset of classes cover the majority of the dataset. In addition, the problem can be framed as a fine-grained classification task, since the useful cues to assess the emotional state of a person are located in small patches and varies according to the person depicted. For domain adaptation, we work without the target labels, a scenario known as unsupervised domain adaptation. In addition, we consider the more strict scenario where access to the source data is not possible. Such a scenario, termed source-free unsupervised domain adaptation, has recently emerged and represents a more realistic adaptation case. Since in this work we use sensible data, we consider the scenario for privacy reasons. In this slide, we present a masked-out version of our proposed architecture, where each block represents a step in our pipeline. Noticeably, the pipeline is split in 3 stages, where the first one comprises 2 parts. In the rest of the presentation, I will introduce each block individually. Overall, our contributions are threefold. First, we propose CLAP, the first method for source-free unsupervised domain adaptation for facial expression recognition. Such a method exploits self-supervised learning for pre-training and our novel pseudo-labeling scheme for fine-tuning, which represents our second contribution. Based on clustering, our pseudo-labeling technique introduces both a score function and a refinement step to select more reliable samples. For our last contribution, we test our method on different FAIR benchmarks. The results show that our method achieves consistent results among benchmarks and classes, and interestingly, CLAP also achieves comparative results with UDA methods that have access to the source data. In the first stage of our pipeline, we aim at first assigning pseudo-labels to samples and then select the best subset for adaptation. Here we focus on cluster assignments. For this purpose, we retrieve the embeddings of the target data using the source model. Then, we use the source classifier to assign a pseudo-label to each sample. Meanwhile, we also perform overclustering on the embeddings to group samples according to their visual similarity. Now, each sample has a pseudo-label and is assigned to a cluster. From the perspective of clusters, we have that each contains a collection of pseudo-labels, and by counting the pseudo-labels in each cluster, we can discover the most frequent class. By means of majority, we assign a pseudo-label to each cluster. To refine the pseudo-labels, we interpret the percentage of the majority as a score function, which we term cluster purity. Intuitively, higher purity implies more reliable pseudo-labels. We therefore filter entire clusters using the purity score function, and for the purpose, we use a dynamic class-wise threshold. Here, we show the updated architecture of our method, with the first stage completely uncovered. We now move on to the next 2 stages. In the second stage, we pre-train a new architecture on the target data. Here, we diverge from the more common domain adaptation practice of fine-tuning the source model on the target data. Since we work in a source-free scenario, we are not able to effectively separate the domain knowledge from the task knowledge contained in the source model. For this reason, and also for the recent advancements in self-supervised learning, we propose to pre-train another neural network on the target data. This will generate a model with only domain knowledge, in which we will inject the task knowledge using our pseudo-labeled samples. To perform a pre-training, we use SWAV, a recent clustering-based self-supervised method that learns a feature extractor invariant to data augmentations by exploiting multi-views and solving a swapped prediction problem. In the last stage, we use the outputs of stage 1 and stage 2 to fine-tune the pre-trained network for the task of facial expression recognition. We append a classifier on top of the pre-trained feature extractor and apply them both on the subset of samples selected during the first stage. Using the cluster-level pseudo-labels, we train the model for facial expression recognition by minimizing a standard cross-entropy loss. Now the visual representation of the pipeline is complete in all of its parts. To recap, in the first stage, we use the source model to pseudo-label the target data. To this end, we use our novel pseudo-labeling scheme to assign more reliable labels and select the most confident samples. In the second stage, we pre-train a new neural network on the target data using self-supervised learning. And in the third stage, we fine-tune the model using our pseudo-labeled samples. Here we present the results of our method. We test CLAP on 4 different adaptation scenarios for facial expression recognition. In this scenario, we consider 2 source datasets and 2 target datasets. The domain gaps are characterized by a mixture of visual and structural differences. For instance, the AFI dataset was collected from Asian films and therefore it's useful for cross-culture domain adaptation, since other datasets involve mainly European and American people. Another example is the FAIR 2013 dataset, which contains only low-resolution grayscale images and is therefore useful for cross-color domain adaptation. In this table, we report the top 1 classification accuracy on the 4 considered benchmarks. In the first block, we present the accuracies of many unsupervised domain adaptation methods, while in the second block we present source-free alternatives. In this second part, we introduce SHOT as a baseline for source-free unsupervised domain adaptation methods and 2 variations of CLAP that use different pre-training. CLAP achieves high accuracies in a consistent fashion, even surpassing SHOT by 13% in one scenario. Interestingly, in the first 2 adaptation scenarios, our method manages to compete with unsupervised domain adaptation methods. For the first scenario, CLAP falls behind by only 0.03% from the best method, while in the second, it achieves SOTA results by a margin of 0.6%. In these tables, we present the class-wise accuracy of our method and an ablation on the backbones and score functions. In the first table, the 2 variations of CLAP achieves the best accuracies for each of the 7 classes when compared with SHOT, which starts from the source model and fine-tunes it on the target data. In the best case, our method achieves a plus 21% accuracy in one of the classes. In the worst case, it performs on par with SHOT. In the second table, we present the top 1 accuracies on the 4 adaptation scenarios, when we incrementally introduce our score function and the self-supervised pre-training. Again, the results are consistent among settings, and the addition of each part improves the performance when compared to the previous row. To conclude, we propose CLAP, the first source-free unsupervised domain adaptation method for facial expression recognition. Our method exploits a novel pseudo-labeling scheme based on clustering, which provides more reliable labels and samples. In addition, CLAP exploits the self-supervised pre-training with SWAV to generate a feature extractor independent from the source data. Last, our method achieves consistent results among scenarios and is even competitive with domain adaptation methods that have access to the source data. Thank you for your attention.